Hi, thank you, Valimir, for the introduction. And hello, everyone. First of all, yeah, I would like to thank the organizers for, well, first for putting together this lovely workshop and, well, also for giving me the opportunity to talk here. I'm very happy to talk about this work today. Uh, well, I have titled this Stochastic Thermodynamics Meets Expected Utility Theory. And, well, this talk is based on and this paper that got published last year, which was a joint effort with Paul Szczypczyk, Francesco Buscemi, Peter Sirahaya, and Valerius Karani. All right, so I'm going to start with this very general landscape. So we have here stochastic thermodynamics as a field employing tools from probability theory. We also have over here information theory, also a field employing, okay, these tools from probability. And well, we also have like this nice intersection and for which we know that, well, there are very strong results, strong connections between these two fields. And so then, well, the main message that I'm gonna try to drive home today is that it turns out there's actually a third field, which, well, we believe that it could be beneficial for the community to be aware of, which is the expected utility theory from the fields of economics. And so basically, well, taking this approach, it will allow us to reinterpret and also generalize some of these results lying at the intersection. Okay, so in order to do that, okay, I'm gonna start with, wanna spend some time with the fundamentals of expected utility theory, and then I'm gonna move on to apply these ideas to stochastic thermodynamics, and then, well, I'm gonna end up with some conclusions and some perspectives. Uh, all right, so the first part, okay, fundamentals of expected utility theory. Well, the first thing to say is that this is a theoretical framework which was first formalized by von Neumann and Morgenstern in the 40s. Well, economists, they care about wealth. So for them, okay, wealth is a non-negative number, which we can think about it as having units of any currency you like, Japanese yen, US dollars, or British pounds, or whatever you want. Then, well, the main object in this framework is the utility function, which is a real valued function, and which is basically going to tell us the satisfaction that a rational agent experiences when acquiring or earning an amount of wealth W. And well, economists ask for this function to be strictly increasing when considering gains, which makes sense because the more wealth you acquire, well, in principle, the happier we can imagine the agent to be, and well, decreasing for losses. And well, economists, they also ask for it to be twice differentiable for mathematical convenience, but also because smooth changes on wealth, well, should be reflected by smooth changes in happiness. Well, here, this is just a diagram to emphasize that the utility function is representing a rational agent. Then, okay, we just invoke probability distributions. And then, well, a lottery for an economist will be like a pair of a probability distribution and a list of values of wealth. And with this, when we can define the expected wealth, just like this. And then, well, with this, we can start doing things like, okay, having a lottery, for instance, here, and we're going to imagine this as a task in which, well, there is a referee. A referee comes along, and he's going to toss a coin. Whenever it lands heads, the player or the agent is going to have to pay the referee a certain amount, here, 1 million yen. And if it lands tails, well, it will be 0. And then, so, okay, so in this way, okay, we can imagine this lottery as a tax or as a tax game somehow. Okay, that's it. And now, okay, we're gonna make things a bit more complex. Here we have, okay, the concept of a decision problem. And so here again, we consider a referee and a player. And the referee comes along and he's gonna ask the referee, okay, you're gonna have to choose between two options, option A or B. Option A is what we're gonna call a deterministic option, which is just gonna be, okay, the player is gonna have to pay the referee a any specific amount of wealth, in this case, okay, 0.6 million yen. And the second option is gonna be what we're gonna call a stochastic option, which is gonna be, okay, the one that we saw before, flipping a coin, and then depending on the outcome, the player is gonna have to pay either 1 million or zero. And then, okay, given these two options, well, we need to, or okay, the problem that economists they pose is like, okay, how can we solve this problem? So basically, they want to, the idea is that we want to model the way a player will make a decision. So, well, in order to do that, one can imagine that we can assign a number, a value to option A. So in this case, well, it's pretty straightforward. It's basically, since it is a deterministic option, so we can imagine that the value of this lottery is just gonna be, okay, this number, 0.6, which again, since it is an amount that the player has to pay, so we think about this as a loss. And then, well, now for the stochastic option, well, that's a little bit more involved because now we have some probabilities. And well, the way economists, they approach this is, which we're gonna explain in a second, it is called the certainty equivalent, which is basically, okay, a number that we're gonna attach to this lottery. And we're going to say that this number, the certainty equivalent, is going to resolve the decision problem because if we are able to calculate this number, then, well, the player is basically going to choose the lottery that represents the smaller loss as well, which is, okay, something natural that we can think about. Okay, so let's see how we can calculate this certainty equivalent. So again, I just remove the pictures and now we only have the lotteries, the same lotteries we had before. And now, okay, we can make a further analysis, which is this. If the agent chooses lottery A, economists, they will say that the agent is risk averse. And the reason for that is that, well, if we look at expected values of the lotteries, we're gonna get 0.6 here and 0.5 here. So if an agent chooses option A, it means that this player is happier to pay this little extra 0.1. So just to be able to avoid having to pay 1 million. So this agent is happy paying 0.6 so that he doesn't have to potentially deal with paying 1 million. So in that case, in this agent, we say that it is averse to this stochastic option, so it is risk averse. And well, that's what we have here. And then, but then we can now imagine that the referee is gonna start changing the deterministic option. Is gonna increase this number a little bit more. And then, well, at some point, we can imagine there is gonna be a point in which the agent, let's say this is 0.9, and so now the agent is gonna be, okay, well, now this is 0.1.9, and now this is 1. So, okay, now this option doesn't look as attractive as before. So there's gonna be a point in which by increasing this number that the agent is gonna change his mind from option A to option B. So, and this is, okay, this is what we can call the certainty equivalent. So basically it's like a threshold after which okay, the player is gonna change his mind from this deterministic to the stochastic option. And so the way to calculate that is that, okay, well, the main assumption that economists use is that rational agents are, okay, expected utility maximizers when gains are involved. And in this case, because we're talking about a tax game, there will be minimizers when losses are considered. So basically, this means that we need to, in order to solve, okay, this problem, this decision problem, when one needs to calculate the expected utility of lottery A, which is this, then the expected utility of lottery B, which is this, and then here, then we can now say, okay, we can properly define the certainty equivalent because, as we said, it is the quantity that it generates a utility which matches that of the stochastic option. So it is a certain amount of wealth such that for the player in question, it generates the same level of okay, satisfaction or dissatisfaction as the stochastic option. So, okay, so this is kind of the definition of the certainty equivalent. So basically, okay, I'm just rewriting this here. And then, um, okay, so that's what we have here. And then, well, we can take just u to the -1 on both sides. So to be able to extract the certainty equivalent. So we see that, okay, this will be the definition of the certainty equivalent, which, as we can see, depends on, of course, on the lottery in question, PXW, X, and also on the player in question, which is represented by U. So we see, okay, the dependence in this way. Um, okay, so that's how one can calculate the certainty equivalent. And well, the first important thing is that to remember is that calculating the certainty equivalent resolves the decision problem because we can just compare that number to uh, the deterministic option, and whichever is smaller, the player is gonna choose that one, the smaller one. So in that sense, the certainty equivalent resolves the decision problem. And the other thing that one can extract from here is, okay, this condition, which is this one from here, which is basically a characterization of risk-averse players. And one can introduce a similar scenario such that, well, the opposite inequality is going to represent risk-seeking players. I'm going to skip through this a bit. The main message here is that, well, this is something uh, very nice that economists developed in the past century, which is basically a characterization of these of risk tendencies. They, well, okay, with this type of construction, they managed to identify that players behave in a risk-averse manner whenever they are characterized by a utility function which is convex, and they behave in a risk-seeking manner whenever the utility function is concave, and they are risk neutral whenever u is linear. So this is a very nice characterization because it is giving us something very intuitive, which is risk aversion. And it is characterizing that with something like a very concrete mathematical property here. And well, this was done by, as I said, by the economists in the 50s and in the 60s. Okay, so given that somehow risk attitude corresponds to the curvature of the utility function, though, so economists, they have defined measures for risk aversion. This is one of them. There are more. And with this type of measure, one can define a utility, ask for a utility function that leaves this measure constant. And in this particular case, this is the function. And well, okay, so in principle, these are all the ingredients that we're gonna need from expected utility theory. And okay, now we can move on to see how we can apply these ideas to stochastic thermodynamics. I'm gonna go through this a little quick because, well, of course, the audience of this event, you are all experts on these things, so I don't need to put this too much into context. So, okay, we have the second law, which is telling us that average dissipated work is non-negative. And well, this was generalized like starting from the early 90s with this series of wonderful results on stochastic thermodynamics. Like, okay, here the Jarzynski equality, which is a generalization of the second law. And later on, okay, we have the Crookes fluctuation theorem, which explicitly addresses the reverse process probability. So, okay, this is all fine and good. And then, well, now we have, this is some of the connections between stochastic thermodynamics and information theory that I was referring to at the beginning. So we have that using Crookes fluctuation theorem, well, we can see that the average dissipated work um, is given exactly by the Kullback-Leibler divergence. So this is very pretty because, okay, it's giving us something in the realm of thermodynamics to something in the realm of information theory. So this is very appealing. And similarly, later on, it was found that it is possible to define another notion of work. They call this worst case dissipated work, which can also be related to another divergence, in this case, the one that lies at plus infinity. And well, more recently, there has been some generalizations of fluctuation theorems, now taking the point of view of retrodiction. And so admittedly, this was somehow the starting point of this project. Was visiting Francesco in Nagoya, and we were talking about these things. And then, well, we had the following question, given that well, the case for Kullback-Leibler and the case at plus infinity admit nice interpretations in terms of work. We were wondering if it was possible to do something similar for the running divergences. So perhaps we can have something here that is telling us something about work. And we found out that the answer is yes, and I'm gonna walk you through how that is done. So in order to do that, now this is where we merge kind of these ideas from utility theory into stochastic thermodynamics. So we're gonna imagine a decision problem with the following features. So now we're not gonna think about a utility theory of wealth, but now we're gonna think about a utility theory of dissipated work. And now between the two lotteries that we were talking about, now the deterministic option, we're gonna imagine a deterministic process. And the stochastic option, now we're going to imagine a process which is stochastic and it obeys a Crookes fluctuation theorem. And well, with this, the decision problem looks like this. So we're going to have a referee and a player. The player represented by the specific utility function we introduced before. And then, well, the player is going to have some battery. And then, well, okay, now the referee comes along and says, okay, you're gonna have to pay with some energy. So please connect your battery to either option A or option B. So option A is a deterministic process in which, okay, we have a physical system going from initial to final state. And well, this is this is going through equilibrium. So then the amount that the battery is gonna get discharged is something deterministic, and it is given exactly by this number. And the second option is the stochastic process, which is going to be also a system going from initial and final state. But now here we're going to think that this is governed by Crookes fluctuation theorem. So now we know that the amount of work that is necessary here, it is not deterministic, but it fluctuates. So given this, now we can ask the same type of question. We want to resolve the decision problem. So again, the value that the player assigns to the deterministic process, well, here it's deterministic, so this is just the same number. Whilst in the case for the stochastic process, now with the tools that we have from utility theory, now we know that this the value that the player assigns to this process here is given by the certainty equivalent. And then, okay, so then now the point is we need to calculate this. But then, well, we know how to do that. And well, this is the definition, and this is Crookes theorem. And then we are using this specific function, which is the one that leaves constant this measure of risk aversion. And then, as I said, we want to calculate the certainty equivalent. So, okay, these are the function, its inverse. So we can do that. This is the definition of the certainty equivalent. And well, okay, we just plug this in here, and then okay, we calculate. We have a few lines, and well, the nice thing is that we get exactly the Renyi divergence of order 1 plus r. So okay, so in principle, well, this is our main result. That if we calculate the certainty equivalent, which is a concept in economics of dissipated work, which is something from thermodynamics, for a decision problem involving work dissipation, well, we see that the certainty equivalent is exactly given by the Renyi divergence, which is an information theoretic quantity. So we can see here that these three fields, they are interacting very nicely with each other with this equation here. And some nice characteristics of this equation is that, well, we only need to assume the only thing we need to assume is Crookes fluctuation theorem, and that this is valid for all forward and reverse process probabilities. This holds for all, well, for the whole standard line of real numbers. And in particular, we can recover the Kullback-Leibler case for r equals 0, and then we can recover the case developed by Nicole and her collaborators for r going to infinity. Also, well, at the same time, well, this is giving us a nice interpretation of the Renyi divergence in this context of stochastic thermodynamics. And furthermore, it is telling us about the meaning of the coefficient R. And well, these are just some conclusions, some perspectives. And I think that's pretty much all I wanted to say. So yeah, thank you very much for your time.